Welcome to part 4 of the lecture on automatic parallelization. So, we looked at data dependence framework in the last lecture. Let us recapitulate a little bit because it is very important. So, if you look at the loop, let us say the loop nest is of depth j, depth d. There are two statements SV and SW, and both of them have an array reference each. So, the first array reference is x with the subscripts being f1, f2, f3 etcetera, each of which is a function of I1 to ID, the loop counter values. Similarly, SW has another reference to the same array x with subscripts g1, g2, g3 etcetera, each of which is again is a function of I1 to ID. So, the question is whether these two references intersect and access the same memory location. First of all, we are not worried about the type of dependence to begin with. Any type of dependence is okay. First of all, we determine whether there is a dependence at all, and then refine it to see if it is delta, delta bar, delta O, etcetera, etcetera. And in this process, we also, when we find the intersection, we also find the direction vector. So, the subscript functions must be equal simultaneously, only then there is going to be an intersection. For all the subscript dimensions, the subscripts must have equal values, f1 equal to g1, f2 equal to g2 etcetera, fs equal to gs. So, this must happen with the same values of I1 to ID, otherwise the intersection cannot happen. So, we start with the most general direction vector star comma etcetera. We can apply the Banerjee's test or the GCD test at this level. So, if we prove independence at this level, nothing more to do, then there will be no intersection at all. And if there is dependence as proven by the Banerjee or GCD test, one of the stars must be expanded. So, here we have an example with star comma star. Suppose the dependence is proven to be true, it is conservative. So, we expand first star to less than, and then try less than comma star, equal to comma star, and greater than comma star. So, each of these is going to be tested with Banerjee's test. So, depending on which one of these returns independence, we do not actually expand that tree. Suppose this will be obviously always independent, returns independence, because first component is greater than. So, we do not have to do these three tests at all. But suppose this also returns independence, then this will also not be expanded further, only this will be expanded. So, then we test each of these three direction vectors and we apply Banerjee's test, see which one of these is actually true. So, we also defined the complement and product of direction vectors. These are needed to compute psi inverse and so, and psi 1 cross psi d etcetera, etcetera. So, if psi k is this, then psi k inverse is defined to be the complement. If it is less than, then psi k inverse is greater than, etcetera, etcetera. And with the product, we simply take the two direction vectors psi 1 and psi 2, take the products of the components, where the product of the components is defined in this table. So, one of them is less than, the other one is less than, it is less than. If it is less than and equal to, it is nil, that means it is illegal type of direction vector at this point, and so on. So, once we know this, how do we use it? So, we actually compute the product of different direction vectors belonging to the various subscripts, various dimensions have various subscripts. So, we compute the product, which really indicates intersection of all these direction vectors. So, that is done as psi 1 cross psi 2 etcetera, etcetera. If this combination produces any dot entries, then there is no simultaneous intersection of all these subscripts. So, we can say there is no dependence and they will never intersect. But if all the entries are valid, we need to find the actual dependence. So, this can be done by intersecting the direction vector that we get here with the execution order direction vector for that particular construct. So, depending on which type of a loop it is, we would have computed the direction vector psi of v to w by looking at the syntax of the loop. So, we intersect it with rather the omega v to w is the execution order direction vector. So, we intersect it with psi to get the direction vector from v to w, that is we are assuming that now the dependence is from s v to s w, because this is dictated by the omega. Okay. So, if this provides any nil entries, then there is no dependence from s v to s w. Otherwise, whatever is given as the direction vector will give you the dependence from s v to s w. So, in that case we still have not found the type of dependence delta, delta bar and delta O, that is actually decided by looking at the position of the two statements. Okay. So, if the we know flow dependence means S v is on left side and S w is on right side and so on and so forth. So, if some of the entries are nil, then we need to check whether there is dependence from S w to S v. So, we compute psi inverse and then intersect it with omega w to v. W to v again would have been computed using the execution order direction vector, that is what this is. So, we would have computed this as the direction vector of the execution order using the syntax of the construct. So, psi inverse we know how to compute. So, we know how to compute the direction vector from w to v. So, now if all the entries are valid, we add S w delta star w to v and which type of dependence, that is decided by the position of the two references. So, now let us look at the second example. We saw one example last time. So, here there are two loops, but A is a single dimensional array. It uses both loop counters. So, the expression is I star 10 plus j on the left side and I star 10 plus j minus 1 on the right side. So, the dependence equation is 10 I 1 plus j 1 minus 10 I 2 plus j 2 minus j 2 equal to minus 1. Okay. So, that would be, so this is transferred to the left side, that is why this becomes 10 I 1 plus j 1 minus 10 I 2 minus j 2 and this remains on the right side. So, that is minus 1. Now, the GCD test says yes, dependence exists and that would be with the star comma star. Now, we need to apply the Banerjee's test and the dependence framework. So, let us this is how we compute all the required lower and upper bounds for star, less than, equal to, greater than, etcetera, etcetera. So, for both the indices I and j. So, the formulas we looked at in the last class itself. So, once we compute those, we can check the constraints at the various levels. At this level, the constraints are sum of the LBs of I j with star as the direction vector must be less than or equal to B naught minus C naught, and that must in turn be less than or equal to the sum of the UBs of I and j with star as the direction vector. So, this will be easily satisfied. So, we can see that. So, we expand the left. Okay. So, the left star. So, we have less than star, equal to star and greater than star. This is not a feasible thing. So, not possible. So, we stop at this point, whereas here this returns true, minus 99 less than or equal to minus 1 less than or equal to minus 1, that is true. So, we expanded the second star again and checked all the three dependencies using Banerjee's test. Two of them returned false and the one returned yes. So, here again this returned yes and the other two returned false. So, these are the only two direction vectors which may be possible, less than, greater than and equal to, less than. It is not yet decided. So, now there is only one subscript. So, there is no need to do any intersection of the two subscripts at all, okay, since there is only one. Now, the execution order dependence direction vectors are all given for that single loop. We know that S 1 theta equal to less than or equal to S 2, S 2 theta equal to less than S 1, S 1 theta less than star less than comma star S 2, S 2 theta less than comma star S 1 are all possible. So, we are going to actually look at less than, greater than. So, any of these with first component less than will be useful. Anything with something other than less than will return a null entry. So, less than comma star S 1 theta less than comma star S 2 is possible. So, when we intersect we just get the same less than greater than. So, when we look at equal to comma less than, again the unless the first one is less than or equal to or equal to, there is no point in intersecting it. So, we have equal to and less than or equal to here S 1 theta equal to less than or equal to. So, that gives us the same vector equal to and less than. So, all other products are dot values, but there are two of them which are not dot. So, these are indeed the dependencies with these direction vectors. So, we have possibly S 1 delta equal to comma less than S 2 and S 1 delta less than comma greater than S 2. So, the position of the two references already indicates, see for example, S 1 has this on the left side and S 2 has this on the right side. So, it indicates that it is a delta, not delta bar or delta O, and since this has been proven true, there is no need to test S 2 delta star S 1. Okay. So, that is how we use the dependence framework and Banerjee's test to compute the dependencies in more complicated expressions and loops. So, that is about the dependence framework. Now, let us see what can be done about parallelization, concurrentization, etc., etc. So, this statement I already mentioned a few lectures ago. If all the dependence relations in a loop nest have a direction vector value of equal to in a loop, then the iterations of that loop can be executed in parallel with no synchronization between the iterations. So, each iteration, within the iteration the order of statements is going to be the same as in the program. We are not going to change the order of the statements unnecessarily. So, if we do that, if since all the dependencies at that level are equal to, we can simply execute that loop in parallel, no violations will occur. And this is the very profound result, even though it looks non-intuitive. Any dependence with a forward direction vector in an outer loop will be satisfied by the serial execution of the outer loop. So, if an outer loop L is run in sequential mode, then all the dependencies with a forward direction at the outer level will be automatically satisfied. So, this is so even for the inner loops of L. I will show you an example for this, but if the outer loop has a dependence equal to, then whatever is said here will not be true. Even if the outer loop is run in sequential mode, the dependencies may not be completely satisfied. So, let us take this example, I equal to 2 to n, then j equal to 2 to n, S 1 has a I j equal to b I j plus 2 and S 2 has b I j equal to a I minus 1 j minus 1 minus b I j. So, the some of these dependencies are obvious, this a I j and this a I j a minus 1 j minus 1 have a dependence. So, so this is when this is 2, this is 1, this is when this is 3, this is 2, etc., etc. Similarly, when this is 2, this is 1, this is when this is 3, this is 2, etc., etc. So, both these dependencies are carried forward. So, S 1 delta less than S 2 is because of these two references. Then we have this and this, the indices are the same, the subscripts are the same. So, this will have actually an anti dependence with S 2 S 1 delta bar S 2 with both the direction vector components being equal to and equal to. Finally, we have this and this in same S 2. So, this is b I j, this is also b I j. So, this is read first and then written into. So, it is an anti dependence from S 2 to S 2 with equal to and equal to. Let us expand the loop. So, we get a 2 2 equal to a 1 1 equal to etcetera, and for various values of j under various values of I. So, we have a less than in the outer loop between S 1 and S 2. So, that dependence has a less than, whereas for the others S 1 and S 2 it is equal to, and S 2 and S 2 also it is equal to. So, this I loop cannot be run in parallel, it should have been equal to. Now, suppose we run the I loop in sequential mode. Okay. So, even the j loop cannot be run in parallel, because S 1 delta less than S 2 has the second loop second component also as less than. But let us observe something, let us run the I loop in sequential mode. That means, I loop will run like this with j equal to 1, j equal to 2, etcetera, and then I equal to 2 will be run, etcetera, I equal to 3, and so on and so forth. Let us see if we run I loop sequentially, and if we run the j loop in parallel, we have j equal to 1, j equal to 2, j equal to 3, etcetera, all of them running in parallel. Okay. So, that is what it really means. So, all these will run in parallel, all these will run in parallel, but these will begin only after these complete. So, that is sequential for I, parallel for j. So, if that happens, let us see if the dependencies get satisfied. So, between S 1 and S 2 there is delta less than. So, let us see where that is. So, A 22 is here and A 22 is here. So, since this is going to run first and then this, automatically this will be computed first and then this would be computed, and this particular dependence would be automatically satisfied. See that even if we run J's in parallel, it would be only here and not across. So, this will be computed and then used, and this particular dependence would be automatically satisfied. This poses no problem, because it is equal to in both directions. So, we have very little to worry about S 1 delta bar S 2, and that would be only between S 1 and S 2 in the same iteration of I and j. So, that would be automatically satisfied. Then this is also between S 2 and S 2 in the same with equal to. So, that means it is in the same iteration of I and j. So, this will also be automatically satisfied, even if we run j in parallel, there will be nothing wrong. So, when we ran I loop in sequential mode, this second component which is less than also got automatically satisfied. That is what we really said here. So, any dependence with less than direction vector in an outer loop will be satisfied by the serial execution of the outer loop, that is obvious. But then the second one said, if we run the outer loop in sequential mode, then all other inner loops can be run in parallel mode, provided the outer loop had a less than direction vector. So, that is true. So, the outer loop had less than, inner loop also had less than, but once we ran the outer loop in sequential mode, inner loop could also be run in parallel mode. So, that is very important. So, let us look at another example. So, here we have I equal to 2 to n and j equal to 2 to n. So, a I j is b I j plus 2, b I j is a I comma j minus 1 minus b I j. So, we have between S 1 and S 2 we have dependence between these two, and that is S 1 delta equal to comma less than S 2, that is between these two. I and I are the same, j and j minus 1 give less than. S 1 delta bar S 2 and S 2 delta bar S 2 remain the same as before, no change. Now, we can run the I loop in parallel, because the first component is equal to in all of them, okay, no problem. But the second loop cannot be run in parallel, the second loop has less than as the direction vector component. What I want to show you here is, even if we run the I loop in sequential mode, you cannot run the j loop in parallel mode, that is what really is the problem. So, let us say we run the I loop in sequential mode. So, this gets run first and then this and so on and so forth. So, the dependence S 1 delta equal to comma less than S 2 is here, it is between this and this. So, even if we run I equal to 1 and then I equal to 2 etcetera, if we run j 1, j 2, j 3 etcetera in parallel, this dependence will be violated. That is the reason why we cannot run the j loop in parallel mode, and it does not matter whether we run the outer loop in parallel mode or sequential mode. So, if we run the I loop in parallel mode, then these iterations get run in parallel and the j loops will all be run in sequential mode. So, automatically the dependence will be satisfied. Now, let us look at some of the loop transformations for increasing parallelism. What we have seen so far are to check whether existing loops can be run in parallel mode or in sequential mode. We did not propose any transformations which can change the loop and make it possible to run it in parallel mode. So, we know that cycles, that is recurrences, create problems. So, recurrence breaking is one of the loop transformations. So, within that there are many of them: ignorable cycles, scalar expansion, scalar renaming, node splitting, threshold detection and index set splitting, if conversion. So, we will see one example of each. Then loop interchange is a very important transformation, loop fission, and finally loop fusion. So, what are ignorable cycles? It says any single statement recurrence based on delta may be ignored. So, let us take this example: x of I minus 1 equal to f of x of I runs from 2 to 100. So, what has happened is this if you expand this, this becomes x 2 equal to f of x 1, x 3 equal to f of x 2, etc. So, that means there is a dependence. Okay. So, you will have to read this first and then this will be x, let us say I equal to 2. So, this becomes x 1, right. Sorry, this is x 1 and this is x 2, this is x 3 and this is for I equal to 3, this becomes x 2 and this becomes x 3 and so on and so forth. So, we would have read x I first and then written into x I. So, x 2 is read and then written into in the next iteration. So, if this happens, there is a dependence from S to S, but that is an anti dependence. So, what the statement says is, if it is an anti dependence on the same statement, then it can be ignored. That is because even if it is vectorized, the semantics of the statement say the right hand side must be fetched first, evaluated first, and then the left hand side should be written into, and that is precisely what this is really saying. So, there is nothing wrong in and observe that this is reading ahead and then writing into it. Nowhere does it actually read something which has been computed in some other cycle. So, because of that, this is perfectly okay. X 2 to 100 reads all the values, puts them in some buffer and then computes the function f on it, and finally assigns x 1 to 99 to these or assign these values. Okay. So, there is no violation of any dependence here. That is why any single statement recurrence based on delta may be ignored, but it must be delta bar may be ignored. So, what is scalar expansion? Again it is very intuitive. So, let us take this loop I equal to 1 to n, S 1 is t equal to a I, S 2 is a I equal to b I, and S 3 is b I equal to t. T is a scalar, a and b are arrays. So, now it is easy to see that from this is the dependence diagram. S 1 to S 3 there is a flow dependence. So, S 1 to S 3 there is a S 1 to S 3, right, there is a flow dependence, t is computed here and t is used here. But then if you expand this particular loop once, there will be another S 1, S 2, S 3 here, and the next iteration I equal to 2 would have S 1 with t equal to a of 2. So, this t and the next t would be tied together, there is a dependence, that would be an anti dependence, this is reading here and that is writing there. So, we have from S 3 to S 1 an anti dependence with less than. So, this was I equal to 1, the next one would be I equal to 2. So, that is another. Then we have a dependence from S1 to S1. So, again look at the expanded version of this, there would be another S1, S2, S3 with T. So, that T, the T which is in the next S1 and the T in this S1 would have an output dependence, and so that is what is shown here. And obviously, between S1 and S2 there is an anti dependence, and between S2 and S3 there is another anti dependence. So, this is your diagram. It has many cycles, one here and another here. So, this cannot be vectorized, that is very clear. Now, suppose we do not want this problem and we replace t with a vector. So, let us say t becomes t x. So, this is called scalar expansion. T is a scalar, it was expanded to a vector. So, instead of using the same t again and again, we are using different locations of the array T x. So, instead of t equal to a I, we have T x of I equal to a I, and instead of b I equal to t, which is supposed to use the same value of t, we have b I equal to T x of I. The advantage with this is some of the dependencies go away. So, for example, from S1 to S2, the dependence between these a i's remains. The dependence from S2 to S3 between the b i's also remains, but when you look at the output dependence on S1, it disappears because we are not going to write into the same location again and again. This is T x of I, it writes into T x 1, 2, 3, 4 etcetera. It never writes into the same location. So, this particular loop, that self dependence has gone. Then we also do not have the output dependence from S3 to S1. Remember b I equal to t, and then the next S1 would have t equal to a I. So, that anti dependence was present here, but that does not exist here because the same location is never written into in I equal to 2, it would have been T x of 2. So, this S3 to S1 disappears, what we have is just S1 to S3 with delta equal to. So, that is because this and this are the same. So, this is the delta equal to that we are talking about. This code can be vectorized, absolutely no problem. But then during parallelization, we do not need such vectors. What we really do is, each of these iterations is going to run as a thread. That is what really parallelization is all about. So, we say that at this variable t which is here is a thread private variable called temp. So, in such a case the program remains as is temp equal to a equal to b I and b I equal to temp, but for I equal to 1 it is temp 1 which is private to the thread for I equal to 1, and for I equal to 2 it would be temp 2 which is different from temp 1, and temp 2 is private to the thread owning I equal to 2. So, that is how this for all loop executes with the temp as private to the thread corresponding to a particular iteration value. So, if that is so, this particular diagram still holds. Okay. So, we do not have any cycles and it can be run in parallel mode. But then scalar expansion is not always profitable or beneficial. Let us look at an example. I equal to 1 to n, S1 is t equal to t plus a I plus a I plus 2, and S2 is a I equal to t. So, if you draw the dependence diagram for this particular loop, so of course, we have the anti dependence between these two t's. So, that is here. So, what was computed in the previous iteration is used here. Okay. Then we have many other dependencies. So, between S1 and S2 we have this anti dependence a I and a I. So, between S1 and S2 there is an anti dependence. So, that is from here. Okay. Then we have a I plus 2 and a I. So, this is if you have a I equal to 1, you would have a 3, a 1, a 2 A4, A2, A5, A3 and so on and so forth. So, that is a anti dependence from S1 to S2 with less than as the direction vector. So, S1 to S2 with anti dependence, okay. That is another. Then of course, you have this dependence from S1 to S2. So, which is a flow dependence with equal to direction vector. So, that is also from S1 to S2. So, that already exists, okay. So, that is here, right. Then we have so this so there are many dependencies. So, this is, if you expand this, we have another S1 S2. So, there would be another flow anti dependence from S2 to S1 as well. So, we have this dependence from S2 to S1. So, that is an anti dependence with less than direction vector. So, these are the various dependencies that we have in this particular program. Obviously, we have a cycle, right. So, it is not vectorizable. Suppose we do scalar expansion, that is expand this T to an array, you get T x of I equal to T x of I minus 1 plus A I plus A I plus 2, A I equal to T x I. So, with this we get this particular dependence diagram, that is you have these, some of these dependencies remain, the anti dependence is the problem, sorry, the anti dependence here is the problem. So, we have T x I equal to T x of I minus 1 plus something. So, we still have a dependence from T x of I minus 1 to T x I S1 to S1, and now this becomes a delta less than. It was actually a delta bar before, but now because it is an array, we are using the old value and computing a new value here. So, this becomes a delta less than. So, there is another loop here. Otherwise, the previous loop went away. So, delta equal to remains, delta bar equal to remains, delta bar less than remains, but then this also remains, okay. But you should observe that this particular S2 to S1 actually has reversed, okay. So, S2 to S1 there is no dependence anymore, that is a dependence from S1 to S2 with equal to as the direction vector. It was less than before, but now it is equal to, okay. So, that is the difference between this loop and this loop. Some of these dependencies have changed, some of them have vanished, but this loop has changed to a worse actually, it is delta less than and it was delta bar less than before. So, even after variable scalar variable expansion, we still have a loop and this loop cannot be vectorized. So, even though scalar expansion is always legal, it may not be profitable. So, that is the moral of this particular slide. The next one is scalar renaming. So, you have this program with S1, S2, S3, S4. Now, you have an output dependence from S1 to S3, T equal to something and T equal to something here also. So, the output dependence S1 delta O S3 just cannot be broken by scalar expansion. Why? You have T I equal to something here and T I equal to something here. So, they both write into the same location of the array. Output dependence does not vary at all. The trick here is we should actually use a different temporary and not use the same temporary. So, first one becomes T1, the second one becomes T2. So, this dependence is from T1 to T1 here and the second dependence is from T2 to T2. Once we do that, this particular program can benefit by scalar expansion. So, we now make T1 into a vector and we also make T2 into a vector. Automatically, the scalar program can be converted to a vector program with the T2 1 to 100 equal to something etcetera, etcetera, etcetera. So, why is T2 coming first and why is S3, S4, the order why is it in this order S3, S4, S1, S2? Well, that is just that the dependencies have to be satisfied appropriately and that is the reason why we have. So, this S4 is computing something and then supplying it to S1, that is the reason why S3 and S4 come first, and then because S1 and S2 are dependent on it, they come later. Okay. Finally, the value of T is T2 of 100, that should be retained as it is. So, scalar renaming and scalar expansion are two different transformations, and they may be applied together as well. Then we come to node splitting. So, suppose there is a cycle consisting of an anti-dependence. So, if we split a node, we may be able to get away with this dependence, and then we may be able to actually vectorize the program. But then we are going to introduce a new array. So, there is a space explosion possible. So, let us take an example, I equal to 1 to 100. So, S1 is A I equal to x I plus 1 plus x I, and S2 is x I plus 1 equal to B I. So, there is a dependence cycle between these two. So, S1, S1 to S2 there is a delta bar, right. So, x I plus 1 is read here and x I plus 1 is written into. So, that is the delta bar cycle. Between S2 and S1, this is writing into x2, this is reading from x1. Then this writes into x3 and this reads x2. So, that means there is a dependence of the flow type between S2 and S1. So, there is a dependence from S2 to S1 with delta. This is a cycle. We can never get rid of delta anyway. So, if we break this into S1 into 2, let us see what happens. We get S0, T I equal to x I plus 1. So, this part is assigned to a temporary. Then we have A I equal to T I plus x I. So, instead of x I plus 1, and then x I plus 1 equal to B I. So, we have broken S1 into two statements, S0 and S1. Let us see what happens here. So, between S0 and S1 there is an anti dependence for the T I, right, S0 sorry the flow dependence between this T I and this T I. So, that is here, and then we have from S0 this particular x I plus 1 and this x I plus 1 have an anti dependence. So, that remains as it is, and then we have between S1 and S2 we have a flow dependence from S2 to S1. Okay. So, because we broke this node into 2, now the dependence cycle has vanished. So, there is no cycle, both these dependences from S0 and S2 to S1 actually are in the same direction towards S1. So, there is no cycle at all, and this loop can be vectorized now. So, we have T1 1 to 100 equal to etcetera etcetera. So, vectorization works here. So, this is another important in the transformation. Remember, if you have an anti dependence cycle, we can try to break it using node splitting. So, if there are thresholds, sometimes we detect thresholds, they can be used for vectorization as such. So, if you take this program with a loop which has one statement x I plus y equal to x I, if you observe it, once you cross the value 5, you would have written x 6 equal to x 1, x 7 equal to x 2, x 8 equal to x 3 etcetera etcetera. Then we have x 5 plus 5, x 10 equal to x 5, and then you get x 11 equal to x 6. So, you have written x 6 in the first iteration, and then in the sixth iteration you are using x 6. So, that means there is a flow dependence with this, and that flow dependence actually can be somehow gotten rid of by if we detect that the threshold value is 5. So, we divide the loop into two. The first loop runs from I equal to 1 to 20, second loop runs from j equal to 1 to 5, and inside we have x of I star 5 plus j equal to I star 5 plus j minus 5. So, it is the same loop, it is just that we have two loop indices here. So, the index values of x here and here will be the same. they will become the same actually, they evaluate the same as I plus 5 and I respectively. Once we have this, the J loop can be vectorized. So, there is no dependence at the J level. So, we can vectorize the J loop and the I loop is run in sequential mode. So, we have a very short vector, but still something is better than nothing. So, we have reduced this iteration space, rather the number of iterations to 20. So, if here the threshold value is 50, I equal to 1 to 100, A I equal to 101 minus I. So, up to 50 the dependence is in one direction, okay. After 50 the dependence becomes in the other direction. So, because of that you cannot vectorize it as it is, but once you divide the loop into two parts, I equal to 1 to 2 and then j equal to 1 to 50, you can vectorize the j loop and run the I loop in so rather the other way, you can vectorize the I loop and run the j loop 1 to 2 in sequential mode. Okay. So, that is what we have shown here. So, that is about thresholds, and the next transformation that we consider is the if conversion. So, here the problem is you have conditions in the program, and if there are conditions, then the control can flow in any direction. It can, if the condition is true, it flows in one direction, and if the condition is false, it flows in the other direction. Because of this, there is no way we can actually run in vector mode. So, as it is, if there are branches, there can be no vectorization possible. So, a solution to this is to compute the condition also as a vector, and for example, here if A I less than equal to 0, then continue. So, A I equal to B I plus 3. So, if A I is greater than 0, then we execute this, otherwise we just go to the next iteration of the loop. So, what we do is we compute a vector B R I equal to A I less than or equal to 0. So, B R 1 stores A 1 less than or equal to 0, B R 2 stores A 2 less than or equal to 0, and so on and so forth. And then we use this B R I as a mask. Wherever B R I is set as true, the for example, not of B R I is true whenever B R I is false, and it is false whenever B R I is true. So, here we wanted to execute A I equal to B I plus 3 whenever A I is greater than 0, that is whenever B R I is false. So, we added a mask here, whenever this particular thing has not of B R I, that is the B R I bit is set to 0, then the mask for this particular instruction is also set as 1 and the instruction gets executed. So, there must be some hardware support for it. If this B R I is set as true, then not of B R I becomes 0. So, this particular instruction A I equal to B I plus 3 will not be executed. So, there is a mask which executes the instruction if it is set to 1, it does not execute the instruction if it is set to 0. So, with that hardware we can actually vectorize this particular loop. So, B R 1 to n is A 1 to n less than or equal to 0. So, that is a vector, and if not of B R 1 to n, so this is a mask A 1 to n equal to B 1 to n plus 3. So, if this is possible then this masking is useful. Another bigger example, we have 4 sentences and a condition inside with 2 sentences inside the condition. So, if this condition is true, we want to execute both. So, first of all we execute the condition rather compute the condition as a vector. Next we have a masked statement where temp 1 colon n execute d 2 something. Okay. So, in vector mode. Then again we have S 1 A1 to n equal to D1 n plus 1, and another mask statement where temp 1 colon n, C1 colon n equal to etcetera etcetera. So, this reordering of statements is because of this particular dependence diagram, where this C shows control dependence. So, for example, if B I greater than 0 is the condition, S3 and S4 are dependent on it. So, that is why there is an arc from S2 to S3, this is the condition, and S2 to S4. Okay. So, once we have this mask, automatically we can reorder statements assuming that this conditional dependence has gone. So, in other words, this is gone. So, we can execute S2 first, which does not have any predecessors, but then you can't execute S3, you will have to execute S4, which does not have any predecessors now, then S1 and finally S3. So, that is how the conversion of if statements helps in vectorization. Loop interchange is a very important transformation. So, let us understand loop what we really do is if there is a loop I outside and another loop j inside, we actually check whether I or j loop can be run in vector or parallel mode. If it cannot be, then we check a condition and see if the I and j loop can be swapped. So, the j becomes the outer loop and I becomes the inner loop. Now, it may be possible to execute one or more of these loops in vector or concurrent mode. So, that is the motivation for the loop interchange. Now, there are three very simple conditions for simple loop interchange. Loops L1 and L2 must be tightly nested, no statements between the loops. So, all statements are in both L1 and L2, there are no statements in L1 which are not in L2. The loop limits of L2 must be invariant in L1. So, in other words, you can't have the inner loop limit dependent on the outer loop index. There are no statements SV and SW not necessarily distinct in L1, which is the outer loop, with a dependence SV delta star less than comma greater than SW. So, what really has happened is if you try to swap the loops L1 and L2, this dependence this is the intuition reverses. So, we should really get greater than comma less than, which is an illegal loop direction vector, and that is the reason why we should not have such a dependence in the first place if you want to do loop interchange. So, for example, in this loop the inner loop is not vectorizable. So, we have this dependence S to S with less than in the inner loop. Now, if we swap the two loops, I becomes the inner loop and j becomes the outer loop, the dependence changes less than and equal to. So, now the inner loop is definitely vectorizable. In this case outer loop can be run in parallel, but in this case the outer loop cannot be run in parallel. Here the dependence from S to S is less than and equal to. So, you cannot run the outer loop in parallel mode. So, let us see if you can swap. You can, because there is nothing like less than greater than. So, once we do that it becomes equal to and less than, you can actually parallelize the outer loop. So, in vectorization you really have to have only one statement inside the you cannot have vectorize the outer loop, because you cannot run a complete loop in as a vector instruction. Okay, a single in a vector instruction cannot be a complete loop, in other words. And in the case of concurrentization, if you actually have very less work for the outer loop, suppose you vectorize the inner loop. Okay. Now, there is very less work for the inner loop, just this statement. So, there may be too much overhead in executing such iterations in parallel. But once you swap and the outer loop becomes parallelizable, for each one of the iterations, parallel iterations, threads of the outer loop, we have a complete loop, the complete I loop runs in sequential mode. So, there is more work per thread, and therefore, this is desirable for parallelization. So, what is the intuition behind this loop interchange? So, if you have this is the iteration space S11, S12, S13, S21, S22, S23 etcetera etcetera. To begin with these are the dependencies. Okay. So, the 1 to S31 to S32 etcetera, and when we are running sequentially these dotted lines indicate how we go. So, we go from S11 to S12 to S13, then to S21 to S22 to S23 etcetera etcetera. And if you actually interchange the loops, we are going to run in this direction. Okay. So, the other index runs more frequently. So, this is legal loop interchange. Why? In the original case we had to compute S11 first and then S12 and then S13, then S21, S22, S23 etcetera. If you run in this order, there is no dependence between S12 and S21. So, no dependences, the dependencies are all in this direction only. So, if you execute all these in and then come to these and so on, there is no violation of dependence. So, loop interchange is legal. If you have a dependence from this to this, then instead of running in this direction, if you try running in this direction, you will not be executing this before this. So, there is a violation of dependence. So, this is an example of a loop illegal loop interchange, that is you have less than and greater than. This is the kind of dependence you would have. So, you will have a dependence in this direction which cannot permit loop interchange. Loop interchange is not always beneficial. So, if you have a loop dependencies in both directions instead of just one, then loop interchange will still not help you, you cannot parallelize the loop. Whereas, in this case when we said loop interchange is permitted, you could have run this entire thing the outer loop S delta equal to comma less than, right. So, this is the way it was. So, we were running in sequential mode. So, we could run this entire thing in parallel, this entire thing in parallel and this entire thing in parallel, and the dependencies would have been satisfied. So, that is what this really was. So, loop fission is dividing a given loop into two parts. So, you have a single loop here, this loop cannot be vectorized as it is. Suppose you divide it into two parts, so that no violation of dependencies occur, then this loop can be vectorized, but this loop cannot be vectorized, but at least partially you are able to vectorize one part of the loop if not both loops. So, what exactly is the condition for loop fission? If a loop contains statements Sk and Sj, where Sk follows Sj in the loop. So, in other words Sj comes first and then Sk, okay, and there is a dependence Sk to Sj with a delta less than, okay. So, that means there is a backward dependence. So, Sj comes first and then Sk, but the dependence is from Sk to Sj in the backward direction. Then loop fission may not split the loop at any point between Sj and Sk. So, let us see what this really is. So, you have a loop like this, we have the dependence from S1 to S3 and S2 to S3. Now, S2 and S3 are here, sorry, the dependence is from S3 to S2 with a delta less than, okay. That is what this said, this is the way it was. So, we have a dependence from here to here, but S2 and S3 are in sequence, okay. S3 comes after S2. So, if you try to break the loop between these 2 points, there is a violation of the lemma and the loop fission is said to be illegal. How does that show here? Suppose we divide the loop here at this point, okay. Now, this Ci and this Ci, okay, are okay, but whatever is computed in S3 as Ci plus 1 will never be fed to S2 as Ci, okay. So, this entire thing will compute using the old values of Ci and then the new values of Ci would be computed if you divide the loop between S2 and S3, which is illegal. Whereas, in this case there are no such backward dependencies between S3 and S2, there is no backward dependence, between S1 and S2 there is no backward dependence. So, the loop can be cut either here or in both places and it will still be a valid loop fission. The last one is the loop fusion. So, they must have the same index sets, loops must be adjacent, no conditional branches in either loop, IO only in one of the loops is permitted, not in both, and data dependence requirement must be taken care of. So, if you have loops like this and if the loops do not run with the same index set, this is runs from 1 to n, this runs from 2 to n, obviously we cannot fuse these two, but you can make sure that the loop index sets are the same. You can say, for example, this can become if I greater than equal to then d I equal to I star 2 and run it from 1 to n. Okay. So, otherwise you could change the loop 2 as I equal to 1 to n d I plus 1 equal to e I plus 1 star 2. So, you change this loop expression here, okay, subscript expression. So, if we do that, then we can fuse the loop. So, for example, in this case we simply peeled the loop a 1 equal to b 1 plus c 1 and ran the loop from I equal to 2 to n. So, this loop, okay. So, sorry, this loop. Now, this loop also runs from a 2 to n. So, it can be merged with this particular loop. So, illegal loop fusion is like this. So, suppose you have two loops S 1 and S 2. So, if you merge these two loops, what really has happened is the dependence has changed. So, when we had the loops separate, we computed a I here equal to b I plus c I and b I plus 1 equal to d I star 2 was computed here. So, this was actually an anti dependence, all the b's were used and then the b's were computed. But once you fuse the loops, the value computed here is fed to S 1. So, the dependence has really changed. So, because of this it is not always possible to really fuse the loops. You really have to look at the dependence from one loop to another. For example, there is a dependence from S 1 to S 2, it is an anti dependence. This is B 1, B 2, B 3 etcetera, and this is B 2, B 3, B 4 etcetera. And because S 1 is completed first and then S 2, it becomes an anti dependence, whereas when you fuse the loops, it really becomes a flow dependence from S 2 to S 1. So, because of such reasons, loop fusion is not always legal. So, this is just to give you a sampler of various loop transformations that occur in practice. So, this is the end of the parallelization part of our course. So, in the next lecture we will begin with instruction scheduling etcetera. Thank you.